All right. Okay, so we have a question about caches. It says, assume we have the following memory accesses being made by a program A, B, C, D, E, and then A again, okay? And then B, C, D, E, and then A, B, C, D. This is a periodic sequence, okay? Um, so in that periodic sequence, all addresses are cache block addresses, and then above pattern goes on for a long time, let's assume. And assume you have a fully associative cache named CAC, okay, that can hold 4 blocks and implements LRU replacement. Okay, since it's not a direct map cache, LRU replacement or any replacement algorithm is required, but LRU is specifically used for this cache. Okay, so there are 2 questions. Before the question, I would recommend you to draw a table, okay, which is going to tell us the timing diagram of the cache, okay, and it will tell us what's changing and what's not changing in the cache. Okay, so there are 4 blocks, so make sure that each column has 4 blocks in it. Okay, here we go. All right, so this says what will be the hit miss ratio of CAC in this steady state. Okay, so we have to first go through all these requests, all these addresses, and made by the CPU to the cache. So in this case, this is time, okay, and these are cache blocks. Usually, you can name them if you like 0, 1, 2, and 3, okay, and it's fully associative, so any address can be written in any block, okay? So this is t equals 0, t equals 1, t equals 2, and anything changes in the cache, we will use in the next column, okay? That's how we represent the cache contents, right? So you can call it cache contents, okay? Now let's start the process. We have A coming in, right? This A, well, all blocks are empty, so you can choose any one of them, okay, to write this A. Let's suppose the top is written. And then we have B, right? Well, since it's least recently used, if you recall, we can use this shifting, okay, to be able to say, oh, this is the top of the stack, top of the cache, and this row is the bottom of the cache, so you can name it. This is again convention. So it's top of the cache. Always have the most recently used, and bottom of the cache is here, bottom of the cache, which always have the least recently used. So when you want to replace any address, you go to the bottom of the cache and then replace it. Okay, if it's of course a cache miss. So A now is in the second row and B now is on top because B is most recent, and then A, B, C, and then A, B, C, and D. All right, so it fills up the cache. The cache is full. Now the next item is E. Well, there's no E, right? So it's a cache miss. We want to replace, right, one of them. Well, we will replace A because A is the least recently used item, and this is most recently used item. So A is going to be replaced. But what that means is that B has to shift to left to one row below, so that becomes the least recently used now. C, D, and E is here. Okay, so we have to keep track of the misses, by the way. So this is a miss, right? This is also a miss because B is not here. This is also a miss, right? This is also a miss, and this is also a miss, right? All of them are misses. So let's continue. So now C is here because now A is requested, right, after E. Well, A, you don't have A in the cache. So that means this is C, this is D, this is E, and then A. So that's another miss, unfortunately, okay? And if you continue doing it, but it's going to be since it's periodic, you will basically repeat the same pattern again and again. But I'm going to go into one step forward to show you that this is D, this is E, this is going to be A, and then next one is B, so B is going to be here, okay? So another miss, all right? So it's going to go on like this. So, as you can guess, that you will never have a hit for this particular case, which means what will be the hit-miss ratio of CAC in the steady state? Well, that means hits are 0, hit ratio is 0, compared to miss. Miss is, you always miss, right? So miss is going to be large value. Let's say the program, the number of data accesses you make, let's say n. So that means 0 over n is 0, right? It's just always missing. So let's go to the next question. Imagine another cache called TAT. Okay, what should be the capacity of TAT to make miss-hit ratio equal to hit-miss ratio of the CAC? In other words, CAC always misses, right, and 0 hit. Then this TAT, as I understand from this question, must always hit. So hit ratio must be 100%, okay, because it's exact reverse, and miss ratio is 0%. So you never miss, you always hit. And how are we going to achieve this? Well, it's pretty easy because you basically, A, B, C, D, you have a periodic request pattern, okay, which is 1, 2, 3, 4, 5, and then another 5, and another 5, another 5. So you only have to make sure that there are 5 empty blocks in the cache. So in order to make sure the hit becomes 100% and miss is 0%, that means you have to make sure your cache has 5 blocks. So TAT has to have 5 cache blocks, okay? It's just an option. If you've got 6 cache blocks, that's also fine. But we're trying to minimize the cache size because it will cause lots of chip cost. It will increase the power. The chip size may be increased. Because you need to put more memory into the chip. So considering that, you have an objective. Objective is to make sure the hit is 100% and miss is 0%, and you achieve that objective with the minimum number of blocks, which is 5 in this case. Okay?